For this example, we have two systems of linear equations in A and B. Each of these systems has two linear equations. And I'm going to solve these, outlining our steps using operations that we can apply that won't change the solutions to the system. So these are things like interchanging the position of any two equations, replacing an equation with a non-zero multiple of itself, and adding or subtracting a pair of equations to obtain a new equation. So this is essentially the method of elimination that you probably have seen before. So I'm going to call this top equation in A, E1, and the bottom equation E2. So for example, interchanging the position of these two equations, putting E2 first on top of E1, well, that wouldn't change what the solutions of this system are. Okay, so we're going to work our way through here. And one thing that I could do that might make things easier in the end is I am going to replace equation E1 with 1/2 E1. So in other words, I'm going to multiply 1/2 times every term in the top equation. And so that's going to give me, in the top equation, x minus 3y equals 10. And I'm going to leave the equation 2 alone for the time being. Now I want to eliminate the x's in the second equation. So to do this, I'm going to replace the second equation, E2, with minus 3 times E1 plus E2. And so that minus 3 times E1, when I add it to E2, is going to cancel the x in the second equation. So this time we're not doing anything to E1, so that stays the same. And now E2 I'm going to get by taking minus 3 times E1 and adding it to E2. So down below, minus 3x plus 3x, that gives me 0. Next I take the minus 3 times the minus 3y, which gives me 9y plus 2y, and that gives now 11y in equation 2. And multiplying the minus 3 times the 10, that gives me minus 30 plus 8. And so the constant term in equation 2 is now minus 22. And now we can see what the solution would be, what y needs to be to find the solution from the last equation down here, E2. But to take this one step further, to really make the solutions clear, I could replace E2 with 1/11 E2. So I'm going to multiply equation E2 by 1/11, and now equation 1 is x minus 3y is 10, and equation 2 becomes y is equal to minus 2. And so when we have the equation written in this form, we'll define this more clearly on the next slide, but we call this form of a system of equations the triangular form. And when we write it in this form, since the second equation has no x's in it and the coefficient in front of y is 1, I could see very clearly that this has a solution which has y is equal to minus 2, and then plugging this and substituting it back into equation 1, I can solve for x. So in other words, I would get x minus 3 times minus 2 is equal to 10, which gives us x is equal to 4. I would get 10 minus 6 is 4. So my solution is xy is equal to 4 minus 2. And we can check our solution. Not a bad idea to take this take these values for x and y, plug them back into the original equations and make sure they satisfy both of those equations. And we'll clean up this notation in a second, but since here we have exactly one unique solution, we say that this system is consistent since it has a solution, and we say that it's independent since there's only one such solution. So with systems of equations, you may recall it's possible that there is no solution. It's possible that we have more than one solution. In this case, we have one solution, so we call it a consistent independent system. Okay, so in part B, we're going to do the same sort of procedure. And so here, again, I'm going to call the top equation E1 and the bottom equation E2. So to get this process started, I want to make the coefficient in front of x in the first equation 1. So I'm going to divide equation 1 by minus 5. So I'm going to replace E1 with minus 1/5 E1. And that's going to give me x minus 2y is equal to minus 3. And the second equation is still 4x minus 8y equals 16. And now we're going to cancel, we're going to eliminate the x term down here by multiplying E1 by minus 4 and adding it to E2. So in other words, we are going to now replace E2 with minus 4 E1 plus E2. So E1 is x minus 2y equals minus 3. And now I take equation E1, multiply it by minus 4, and then add it to the second equation. So the x's cancel. I get up here 8y minus 8y, so the y's also cancel. So on the left side of the equation, I get 0 since all of the terms cancel on the left side. And on the right side, we get minus 4 times minus 3, that's 12. And 12 plus 16 gives us 28. And now we see something strange, which is this weird contradiction over here. So this is certainly not true. 0 does not equal 28, and there's no values of x and y that are going to make this equation true. So that tells me that this system has no solution. And that happens sometimes. And that means we would call this system inconsistent. So when a system of linear equations has no solution, we say that it is inconsistent. And what's going on, if we were to graph these two lines, we would see that there are two parallel lines that don't intersect each other, and that's why we have no solution. So in question A, part A, we saw that we had one unique solution, so that system was consistent and independent. In B, we saw that this system of equations has no solution, so we call that inconsistent.